Hello, everyone. This is Stephen Massa with the Water Environment Federation. I want to welcome each of you to the next generation of phase-activated sludge technology with model predictive control e-showcase. Before we begin, I would like to quickly review a few logistics. During this webcast, while you cannot speak directly to the presenters, you will have an opportunity to submit questions by typing your specific question into the GoToWebinar pane that appears on the right-hand side of your computer screen. I will be accumulating questions and will direct them to the presenters at the end. The PDF PowerPoint presentations are now available for downloading at WEF's website and are currently available in the Handouts pane of the GoToWebinar panel. This link was included in the GoToWebinar reminder email sent an hour before the webcast and will be included in the follow-up email sent 24 hours after the webcast has ended. We will be recording this e-showcase. The recording link will be available on the webcast website 24 hours after the webcast has ended. PDH credits are not available for this event. Please note that today's event is an e-showcase and does not necessarily reflect the views of the Water Environment Federation. If you have any additional questions after the webcast has ended, please email webcasts@wef.org. Today's speakers are Mark Drake and Peter Earls. Peter Earls graduated from Iowa State University in 1981 with a BSCE. He went to work in Kansas for a large engineering consulting firm and designed everything from bridges to water and wastewater projects to street and drainage projects. In 1992, he started his own company with just 2 people. 28 years later, Mr. Earls has 30 employees with 4 offices in Kansas and 1 in Oklahoma. Mark Drake has been a water professional for over 20 years. He obtained his BS in chemical engineering with an environmental emphasis from Iowa State University. Mark has held PE designations in Wisconsin and North Carolina and became an LEED accredited professional in 2008. Mark has been a part of the Veolia team since 2010 as a product manager for biological products and as product champion for the AQUAVISTA line of digital solutions. Mark is also very active in the North Carolina AWWA-WEA, where he currently serves as both Schools Council Chair and as the Chair of the Wastewater Operator School Committee, and he also teaches several classes for treatment facility operators. Mark, I'll hand it over to you.
Very good. Thank you, Stephen. Thank you, everybody, for joining us today for this e-showcase presentation on the next generation of phase-activated sludge technology with model predictive control. The agenda for today is up on the screen. We'll walk briefly through what phase-activated sludge technology is and review some of the characteristics of that type of technology. And then we'll move into a bit of case study information, and we'll talk about the Liberal Kansas project. That is a project designed by Earls Engineering, and Pete will take you through some of the drivers for that project and the solutions and how they went about making some decisions on that project. And that will lead us to a look at the latest generation of phased isolation technology, which is the type of phase-activated sludge technology. And then we'll move into the controls side of things. And we're going to talk about model predictive control and specifically AQUAVISTA Plant, which is the Veolia solution for advanced model predictive control in treatment facilities and sewer collection systems. And then hopefully we have some time at the end for a few questions. Okay, so what is phased activated sludge technology? It makes sense to just quickly walk through a couple of different types of activated sludge technology to define that. First, I assume most people on the webcast are familiar with conventional activated sludge technology. Here's a typical flow scheme for an MLE activated sludge process with an anoxic reactor up front, an aerobic reactor, and secondary clarification. We have return activated sludge to bring the biomass back and build it up to the level we want it to be at in the system. And then we have an internal mixed liquor recycle to bring nitrates from the aerobic zone back to the anoxic zone where they're denitrified. A couple of key characteristics of this type of conventional activated sludge process are that it is a continuous flow. What comes in generally passes through all the reactors. Each reactor has a specific function, and then flow exits the system. In that sense, it is continuous flow, and it is not a phased system. Another type of activated sludge system that is prevalent in this in the treatment world today is an SBR system. That's showing up much dimmer than I would have expected it to, but hopefully you can kind of see the, there we go, the typical cycles that a typical sequencing batch reactor goes through. So distinguishing characteristics of this are that it does not use external clarifiers. All of the settling and clarification happens within the reactors themselves, along with the treatment. So it's walking through, it has aerated steps, it has non-aerated steps. We'll go back and forth between those phases to achieve the nitrification and denitrification necessary for the process. And at some point, it will settle the biomass in the reactor and draw the clear liquid off the top. And there may be some idle phase at the end. We can describe these types of processes as batch, flow, and phased. And phased mainly in terms of the aeration or non-aeration that's happening. We're not segmenting anoxic functions into their own reactor and aerobic functions into their own reactor. We're doing those functions all in the same reactor and varying it based on time or other factors. And that batch flow may be just the effluent, or it may be the influent and effluent. There are many SBR systems that take continuous influent and intermittently discharge, and then there are batch systems that take intermittent influent and intermittently discharge. But they all do have settling and decanting in the reactors, and thus are discharging flow on an intermittent basis. So they're batch flow from that standpoint. So when we look at what we're referring to when we're talking about phase activated sludge technology, in some ways we're somewhere in between these two types of conventional systems that you see. A phase activated sludge technology, as we define it, is a continuous flow technology, continuous influent, continuous effluent. It's using conventional secondary clarifiers to achieve our solids liquid separation. But we are phasing within the reactors themselves. There are not separate dedicated anoxic zones, anaerobic zones. And so we are walking through aerobic steps and anoxic steps to achieve the nitrification and denitrification we achieve within the system. And we are also controlling how the flow proceeds through. So we're in essence phasing the flow, although it is continuous across the whole system. We're phasing flow between series and parallel type operations or isolation type operations. The phases that you see here, phase B, E, G, J, those are some general typical phases used in this type of control strategy. There are numerous intermittent phases. You can imagine any combination of where the flow is coming in and which reactor flow is leaving, and whether a reactor is in an aerobic state or an anoxic state. And there's a phase that lines up with that combination. And so depending on our specific treatment objectives, a particular facility may incorporate many more phases than just these 4 basic phases you see here. And then there are systems that will only utilize these 4 basic phases. Every system that goes in should have the flexibility to adjust those phases as needed based on their real world load situations. And we'll talk about how we do that automatically and how that can be optimized with more advanced systems when we get to the controls portion. So another way that we refer to this continuous flow phase technology is phase isolation ditch technology. From our company, that has been utilized the trade name of BIO-DENITRO for many years. Technology has been out there and known as phase isolation ditch technology. As you can see, that schematic shows oxidation ditches, which is how this has typically been applied in the past. And when we look at how we physically set that up to achieve the functions that we're trying to achieve, we usually would see some form of distributor at the front. This may be a simple distribution box with an automated gate that controls which reactor the flow goes to. It could be weirs on the front end of each of the reactors. And then there are weirs on the effluent side of each reactor to control whether that reactor is discharging flow or not discharging flow. And then there is a connection in between those reactors for flow to pass between them. And that's what allows, when we lower the weir in one reactor, raise the weir in the first reactor, and bring flow into that reactor, we're creating a hydraulic gradient to send flow from one reactor to the other one and out. And so we can manipulate very simply the influent flow control device and the effluent flow control devices to send flow through those reactors in any direction that we want. We can isolate a reactor and only treat for a period of time, and isolate a reactor and settle for a period of time if need be in certain storm flow type situations if we want to inventory some sludge in a reactor. So it imparts a great deal of flexibility in how the flow is processed through the system. The typical arrangement utilizes surface aeration rotors in this ditch configuration. That's how hundreds of facilities out there have been done over the last 30 plus years. And it is a simple solution that mechanically has worked well, but it does leave something to be desired in terms of aeration efficiency and footprint, because they tend to not be the deepest of tanks. And so that's where we'll see some improvements as we move forward here. So some of the common characteristics of these types of systems, the phased isolation technology systems, I can get this to advance, are the phasing between aerobic and oxidant conditions, the phasing between series, parallel, and isolation operation. They all tend to operate in the extended aeration mode of treatment with hydraulic retention time, usually in the 18 to 24-hour range, and an SRT of 12 to 20 days. One of the real key characteristics that makes this very advantageous technology is the ability to do TN removal to low levels without internal recycle. So there is a energy benefit to not utilizing pumping to move nitrified flow around the system. The manipulation of the flow path and the environment within each reactor allows us to achieve that, similar to certainly how an SBR goes through its cycles and does not require any sort of recycle of nitrates back to any different reactor. Again, they do use conventional clarifiers. There are offshoots of this type of technology that do function on a more of an SBR, continuous SBR type basis that we have done, usually for very, very small plants. But predominantly this technology utilizes conventional secondary clarifiers, which is good from the standpoint that they are easily designed. They're known out there in the industry and in the consulting community. They have integrated and optimized sludge withdrawal mechanisms, optimized skimming devices. So that's a very, very known commodity to work with the system. And then finally, they all have a time or nutrient monitoring basis for how it determines how it moves through those phases. The traditional method is a time basis that requires, to optimize the plant, regular adjustment of those times. So when we move to nutrient monitoring, then we start getting more optimized, more elaborate. It's still fairly simple with ammonia and nitrate analyzers. And we have solutions that work quite well doing that through PLC control logic. There is a more advanced way to do that, and then we'll talk about that later on in the presentation. So that is, I got one more slide here. Those are some of the key characteristics of phase-activated sludge technology. Here we can see some of the typical design effluent values that we achieve with this kind of technology: around 10 milligrams per liter BOD TSS, less than 1 ammonia, less than 5 total nitrogen, less than 1 total phosphorus when we incorporate anaerobic selectors up front. That is, if we're doing a system and we're targeting biological phosphorus removal, we call that a BIO-DENITRO. without the anaerobic selectors up front. It's BIO-DENITRO. So there's no phasing with those. Those are fairly typical, fairly conventional anaerobic zones up front to achieve the biological phosphorus removal in the system. Sometimes systems do utilize secondary noxic zones with this technology. That is very dependent on the specific wastewater makeup and the effluent total nitrogen target. We certainly have cases, and Liberal is one of those. Liberal, Kansas has a fairly low BOD to TKN ratio in the influent. There really isn't enough carbon present to support denitrification down to the levels that we'd like to achieve. So that facility, as you'll see, does have secondary noxic zones designed into it with the ability to add some supplemental carbon. And then through biological phosphorus removal alone with a BIO-DENITRO, 1 milligram per liter total phosphorus is generally what we would design for. Certainly lower levels are achievable with chemical addition, and particularly filtration is used. The picture here, you can see 12 MGD BIO-DENITRO facility in Cary, North Carolina. Is their north plant. And I just wanted to show a little bit of cost information. I'll make reference to this later as well. Around $3 per gallon, and that's the cost for just the main secondary treatment. That's not the complete plant. That was from an upgrade that they did, adding the third train. And what's really telling about this, and this is from the US EPA Municipal Nutrient Removal Technologies reference document, is the very low cost of total phosphorus and total nitrogen removal. That's achievable with a system that doesn't incorporate the recycle, that has very flexible, finely controlled phasing within the system. So just wanted to note that, and we'll make reference to that later. So with that, I'm going to hand it over to Pete, and Pete's going to tell you a little bit about the Liberal, Kansas project.
Thanks, Mark. The Liberal treatment plant handles, the current one actually handles both city municipal waste as well as national beef packing plant, which is a beef packing plant that's right next door. The Liberal plant was built in 1982 and basically no longer could meet the effluent requirements. They currently discharge about 9 miles through a gravity pipeline to the Cimarron River. So we had to meet the KDH&E regulations for water discharging into a stream. New regulations set up by KDH&E had the new permits limits for lower TKN and brought in phosphorus. These limits were set to 10 and 1, which required the existing plant to be looking at what to do, how to correct these or get the limits down. One of the main concerns was the MVP plant being tied into it. MVP has a phosphorus coming out of their lagoons at 25 milligrams per liter, and ammonia is over 120 milligrams per liter. So the first thing we looked at was to try to find a way to work both plants together to make one plant, basically, and trying to come up with a way to retrofit the existing system. The retrofit we got with Veolia and looking at an MBR plant, and then we got looking into how to retrofit this existing plant to make it work. We get an in-depth look at trying to use the primary clarifiers as BIOPs, and then tried to look at redoing the aeration basins. Once we got into it, we found out that the way it was originally designed made retrofit extremely difficult. And the aeration or the primary clarifiers were fairly small to try to get the BIOP to work. And then as we emptied one of the containers to take a look at the concrete, we found out the concrete condition was poor. So we got back with National Beef and we decided that the best option was to actually build 2 separate plants. The city take care of the city waste and National Beef take care of National Beef's waste, with the city discharging to the river, National Beef discharging to irrigation. So the city started looking at what they wanted. They wanted new technology, small footprint, and they wanted it fully automated. They own the properties directly south of their existing plant, So they wanted the new plant to fit right there so that they could be obviously working on the old plant while the new plant was constructed. And for a time, obviously, both plants would be in operation. So they looked around at a lot of different options. They visited a lot of different treatment plants. And again, they decided to be with Veolia. The BIO-DENITRO process fit the bill of what they wanted. It gave them the technology they wanted, gave them the BIO-P process, being part of the basin, along with the trains, as long as they aerated sludge basins, all in one unit, as you see on the drawing there. Through negotiations with Veolia, Veolia supplied the BIO-DENITRO system, blowers, and the tertiary filtration system. The other part of the system was, of course, the controls. They wanted everything automated. They wanted everything on computers and smartphones. Currently, they have an entire wall that is the current control system from the 1985 plant. So we got back with Veolia because they were the ones that were supplying the main process as well as the other items. And so Veolia got together and designed the SCADA system for the city. Working with the city, we also put in a new administration building, which is that T-shaped building to the top. Obviously, new headworks, clarifiers. We have a centrifuge as well as a tertiary filtration system. As you stated, the various times the city's BOD coming in is low. We have chemical addition as possibilities, or adding micro C if needed, as well as phosphorus removal if needed through the tertiary filtration. The plant was designed and put out for bids. It came in under budget at $30.8 million, currently under construction. The winter slowed it down, but we have the main inflow pump station in. The aeration basin is nearly complete, but we figure the entire plant will take 18 to 24 months to complete. So Veolia met our requirements by giving us the compact footprint, gave us the desire of the technology and the SCADA system that the city was looking for. Mark?
All right, thank you, Pete. So just a little bit more information about the liberal design in some of the upcoming tables. And also, I just wanted to draw notice to the fact that before, when we talked about the phase activated sludge technology and the history with that technology, we have predominantly supplied that in oxidation ditch type reactors. When we approached the design for Liberal Kansas, we did not approach that with oxidation ditches. It's with deeper rectangular tanks with a simple double-sided diversion gate and central channel. You can see that in this rendering. Construction isn't complete, so I don't have a full picture of the completed facility. But this allows us to flow through this channel either way, from one reactor to the other. So they are flowing, in essence, in series from end to end when we're flowing in series. And it is a solution that will allow us to meet the full functionality of the BIO-DENITRO process, obtain all the benefits of the very efficient nitrification and denitrification in the system, and do so with two very simply actuated gate devices. That ultimately leads to a simplified and less expensive construction than doing oxidation ditches and a much smaller footprint. I'm not sure how well the site would have worked with conventional oxidation ditch based phased technology, but this new generation of the technology utilizing deeper tanks, more efficient aeration, works very well on the project site. It does certainly use fine bubble diffusers, much more efficient than the surface rotors that have traditionally been used with this technology when done in oxidation ditches. And that leads to a much lower total operating cost for this system. When we talk about that simplified and cheaper construction and the smaller footprint, that contributes to a 20 to 30% lower total installed cost as well. And in fact, when we look back to the approximate dollars per gallon for from that EPA look and the North Cary construction, and we look at that in today's dollars, it's around $4 per gallon per day for the main secondary system. When we look at the bid form from the Liberal project and dissect that and boil that down to the main reactors and clarification, that is just a hair over $3 per gallon. So we are much more economical with this arrangement of the system and much more energy efficient. You can see here the design flow of the plant is a little over 4 million, 7.1 MGD peak. You can see the BOD to TKN ratio is pretty low with influent TKN that is higher than your typical domestic wastewater at 70. It gets both hot and cold out in rural Kansas, along the Kansas-Oklahoma border. So we are designed for a pretty wide temperature range and designed to handle and treat to the extent required down at low temperatures, as low as 8 degrees C. The effluent we're designed for reaches further than what the current KDHE permit limits are for the surface water discharge, with the total phosphorus down at 1/2 part and total inorganic nitrogen of less than 5 milligrams per liter and total nitrogen less than 8. You can see I'm not going to go through all these individual numbers. You can look back at the presentation afterwards if you want to dissect any of that. But again, here you can see in the main reactor itself, pretty conventional in terms of HRT, SRT, and you can see there that design, and this would be at the full loaded design conditions, design anoxic anaerobic time, about 34% anoxic, 66% aerobic on average. That, of course, is variable, and as we step into the more advanced controls of the facility, that is really the main parameter that is adjusted in real time as the phases are controlled based on a variety of inputs to keep it optimized at all times. So with that, I am going to move into that discussion on the controls. The Liberal plant will utilize the AQUAVISTA Plant's digital model predictive control-based system. So just a brief summary of what that system is. It is advanced optimization for collection systems and water reclamation facilities. We've employed it as a holistic solution that integrates a complete plants and all of the unit operations at the facility and or collection systems, or down to just the secondary process. So it's fairly flexible in the scope and size that it can be applied with. It is model predictive control. There are algorithms that are developed that have been fine-tuned over many years and utilized in treatment facilities and collection systems that incorporate both hydraulic and process models and economic models to drive the optimization of the system. So there's various inputs from real-time sensors at the plant to weather data to energy price information that can all go into the system and feed the optimization. We've applied it in municipal plants and industrial plants, and it's not only applicable to Veolia technologies. We apply it to a variety of different technologies, and I would say the most predominant would be a conventional activated sludge plant. There are certainly more of those out there than anything else, and we've utilized AQUAVISTA Plant advanced controls in many of those kind of facilities. And then finally, it builds on over 25 years of experience with advanced controls. Our team, predominantly over in Denmark, has been perfecting the algorithms that are used for, again, over 25 years. They really pioneered this use and continue to promote it today. AQUAVISTA Plant is process control from the cloud. All of the algorithms that are running and the generation of the model, that is all happening in cloud-based servers. So we're pulling information from PLCs at the plant. There's an OPC bridge, firewall protections, etc. The highest level of security that you could employ is employed with the system to ensure the plant's network and the plant's equipment are protected. But we're pulling the necessary data that needs to feed into the algorithms, and utilizing that information and generating new set points. And those set points then go back through the OPC bridge and are implemented automatically in the PLC or PLCs, depending on the overall scope at the plant. We traditionally, with this arrangement, will set up on-off controls in the plant SCADA, and we'll certainly do that for Liberal, Kansas, where the operators always have control, and at any given time, a particular feature of the system can be turned on or off by the operations staff through their SCADA system. But then in addition to that, there is its own user interface that has all the tuning settings for the algorithms, and you can certainly turn things on and off, and there is its own trending and viewing the models and viewing various key performance indicators, all housed within the AQUAVISTA Plant user interface. And that is a browser-based interface that operations staff can access from any internet-connected device, their phone, their tablet, their computer. So it makes it very easy for staff that are out there in the field, in the plant, to be following things and checking and making adjustments, et cetera, on the fly. So just a quick look at the structure of a typical algorithm. There isn't anything new or novel in terms of this aspect. And to be clear, I am not a data scientist and I am not a coder. I am a process person and product manager now. But many people at Veolia are data scientists and coders, and they have worked and developed these for many years. So we have various online instruments. We have external information like weather forecast information, weather radar, energy price information. That all is filtered through a set of data quality checks. As we all know, the algorithms that run, the outputs that they generate, they're only as good as the data that feeds into it. So there's a very robust data quality checking system that will be able to identify when there is data coming in that doesn't make sense, and that data will be filtered out and not used, or some form of action automatically be taken. And we'll see a little bit more on that in just a second. But all that data feeds in, goes through the data quality check. The various models that the different modules utilize are built, they're updated. That model predictive piece of it, and then the raw data that's come in, all that goes through a pre-processing step. And then there are the algorithms that are running the control logic, and there are different ways that it does that, depending on the type of module and the type of control in place. And it is crunching the numbers and utilizing that data and the model predictions, and then ultimately leading to, after some post-processing, here are new set points for the system. And that's happening on a continuous basis. And those new set points are sent back down to the PLC every minute or two. So those types of advanced model predictive control algorithms can be applied in all kinds of different areas in a wastewater treatment plant and in a collection system. For the Liberal Kansas project, the focus there is on the secondary treatment, and it's on utilizing the DO and nitrogen control module and some of the other secondary treatment modules to ensure that that process is very well optimized at all times. As we developed this project with Earls Engineering, one of the key concerns was this new technology and the ability of the operations staff to optimize it on their own. And the one thing that I think many of us have seen and felt throughout our industry is the frequent turnover of staff, the learning curve in place as some of our experts who have been running plants for a long time are retiring and newer people are coming in. Having a more robust, more automatically optimized facility makes those transitions easier that we're seeing in our operations staff today. So we apply AQUAVISTA Plant in all these different areas within a facility, and we're continuously growing the number of modules that are used out there in our treatment systems. Many of these modules work well together, and as you add more and more, let's say the machine learning aspect of it gets better and better, and the algorithms refine the control better and better. For example, in a secondary system, implementing the DO and nitrogen control module will control that part of the system well, but if you also implement the RAS control module, the solids retention time module, the flow distribution module, and the air supply module, all of those individual modules will operate even better by having the other ones alongside of it. I wanted to do a very quick example of NDN phase control. The important takeaway with this is that it is a multi-criteria control. We're utilizing flow, ammonia, and nitrate and DO as inputs to the algorithm. And the basic strategy is we want more nitrification time, more aerobic time when loads are higher, and more denitrification time when they're low, so that we're not over aerating. The benefits are maximizing the nitrate removal, maximizing the nitrate that's used for BOD removal, improving the nitrogen removal, and getting the highest energy efficiency possible in the system. This is just some photos showing some actual information, some data that's come out of the system. That first one, again, we're building that model. We're utilizing that in our control of the plant. This also enables us, it's a very routine setup in all of the control modules that we are making adjustments, factoring in lag time. Again, every time you call for a change in a plant, it takes some time before the effects are felt, and through our historical model that's built, we know how things are going to behave. I should say the control system knows how it's going to behave, and it can compensate for that to keep things more fine-tuned and automated. This just shows an example, and this is in a plant that was utilizing the technology back in around 2000. So we've refined it quite a bit since then. But this just shows a plant that's even doing incredibly well at removing ammonia and nitrate, with average levels less than 1 on ammonia in the effluent and right around 2 on nitrate. Once we implement the DO and nitrogen control module, it gets even tighter, even better control. So you can imagine how well that does for a facility that's not already treating that well, and moving down there. I mentioned the automatic data quality checks. I just wanted to come back to that topic real quick because this is important in any facility that's utilizing this type of automated control that is implementing new set points. When we have data that is not usable, not able to be used in the algorithms, and if it would generate set points that are potentially going to lead the system astray, it won't use that data. And there are many different fallback positions that the system automatically uses once data goes away. It doesn't immediately go, okay, well, we're not going to control the system now and everything just goes offline. It's going to use the next best, the next best, the next best. It's always going to optimize it as good as it can with the information available to it that is good information. So at the end of the day, when we implement this type of model predictive control, the results that we've seen in treatment facilities, and this includes very large facilities like the 2 million, or the facility in Warsaw, the largest plant in Warsaw, Poland, that treats the wastewater from 2 million people, to smaller 10,000 population equivalent plants. Very significant energy savings, chemical dosage savings, better gas production from digesters, and most importantly, lower effluent concentrations and more stable systems. We also see gains in capacity in treatment systems where this model predictive control is implemented, the ability to get higher BOD and ammonia loads through, and sometimes avoid additional reactor construction. And the same on the hydraulic side. We certainly have examples of large facilities that have avoided building additional secondary clarifiers, or have significantly reduced the size of clarifiers used in their design by some of the strategies that have been implemented with this model predictive control. Last thing to mention on that, one really neat feature with the AQUAVISTA plant, we do utilize what we call AQUAVISTA Lab, and that is a user development platform where the facilities that implement that solution have the ability to design new control algorithms themselves, working in conjunction with us ideally. But it's sort of a playground where if there is not a control module that is already ready to go, if a plant sees a need, they can move in the direction of doing it themselves and come up with their own control algorithms, build their own models in real time within the AQUAVISTA platform, and test out their control algorithms on their own in that virtual environment before anything is ever implemented. It's a pretty neat, powerful tool to enable facilities to really expand what this type of control system can do. And so with that, I think we've left just a couple of minutes. I'll turn it back to Steve and see what we might have for any questions.
Okay, great. Thank you, Mark. Yeah, we have several questions in. Unfortunately, we're not going to be able to get to them all. I do want to let everybody know that we will forward these questions on to our speakers, and they can follow up directly with you after the webcast. So don't worry if we don't get to your question live today. They will be forwarded on to our speakers. Okay, so the first question that I would like to start with. So we have one question. Is TP removal below 1 mg per L achieved biologically?
So the answer to that is yes, it certainly can be, and it is in many cases with the BIO-DENITRO system without any chemical addition. It is, of course, dependent on the makeup of the incoming wastewater. If flow is, or if the influent predominantly has a total phosphorus content that is, say, 12 milligrams per liter, but the BOD happens to be low, that facility may not. But typical conventional type 250 BOD, 6 or 7 TP, maybe 8 TP coming in, that facility can absolutely achieve 1 milligram per liter without chemical addition.
Okay, excellent. And I think, unfortunately, we're just going to have time for one more question, but we will, as I said, forward these questions on. Can AQUAVISTA Plant be applied to smaller facilities?
So AQUAVISTA Plant can be applied to smaller facilities. It really shines in larger facilities. I mentioned the plant in Warsaw, Poland that is serving 2 million people. There is a very large plant, the largest plant in Milan, Italy, is currently implementing AQUAVISTA Plant. That is up for GWI Smart Water Project of the Year award. So it's really shined in very large plants. But there are facilities as small as, 1 MGD, 2 MGD. Once we get much smaller than that, those facilities, the amount to be gained is becoming less and less. So it gets harder and harder for it to pencil out from a financial standpoint. But it all comes back to what a particular facility is trying to achieve with it. If the goal is operation cost savings, and that's all that is cared about, really small facilities, there's just not enough there to save. But if the goal is, hey, we have compliance failures frequently, we need to be able to put this plant on autopilot and know that we're going to achieve the effluent we're supposed to achieve, that can happen in any size facility, and it would be very applicable with that type of driver in place.
Okay, great, excellent. Well, thank you again to Mark and Peter for your thoughts today and your presentations. We really appreciate it. And thank you to everyone who attended today. Look out for the follow-up email that will go out tomorrow that will include a link to this webcast recording if you'd like to share it with anyone. And we hope to see you at one of our next webcast events. Thank you so much.